on lighting approaches to maximize profit, LAMP. We're going to feature some lightning talks from a few graduate students today, and I'm going to welcome you all here with a little bit of information about GLAZE. GLAZE is the Greenhouse Lighting and Systems Engineering Consortium based out of Cornell, and we're here to transform greenhouse lighting and systems management to support climate-smart, controlled environment agriculture. We do so by conducting research and educating growers so that emerging technology can be adopted faster and help growers save money and reduce the environmental impact of energy use in greenhouses. Our research, as I mentioned, is focused on greenhouses, but also indoor agriculture, and we seek to help technology transfer through showcasing the results of technology's impact on plants. We also do things like webinars, short courses, and help educate the workforce in a variety of ways. And our membership values our networking benefits by meeting in person at member meetings and our annual summit. Our members are very valued, and we hope that you're interested in potentially joining. If you would like to join, you can contact me about the membership benefits for this year's membership. And this year we have a new membership initiative. We have now created a individual membership benefit called Vivid Canopy, where folks who are working in the CEA industry can connect, and CEA organizations can show how they're leading by example and hiring a more diverse workforce. Save the date for the GLAZE Summit and consider registering. We just opened registration last week and are excited to have our next event in Montreal. And the theme is dynamic lighting. So thank you to our anchor partner, Saloom. We're currently recruiting a couple other sponsors for our keynote and our networking event. And we look forward to seeing you potentially in November this year. Today, we're here to learn from LAMP. So I'm excited to learn the results of 5 different research studies and hear how the industry can adopt some of the insights from these studies. Thanks, Neil, for taking over with the slides.
Thank you for joining us today, everyone. I'm Neil Mattson. I'm a professor at Cornell University, and I'm one of the faculty members working on Project LAMP, which is lighting approaches to maximize profits. And LAMP is funded by the USDA. It's a multi-state, multi-institutional project where we're trying to improve our understanding of crop lighting so that CEA growers can reduce production costs and have more control over crop growth and quality. So we've had probably over a dozen graduate students that have come through working on LAMP projects, and we have 5 of them today that are each going to be giving about a 7-minute presentation. And then from there, we will collectively do Q&A with all the grad students. And so I'll introduce each student when it's turn. And then I do want to point out 2 of our students are actually in South Korea for a lighting and horticulture conference. So they are going to, they have recordings. So we'll start out with one of those. So our first up is Song-Jun Jung, who is a PhD candidate in the Department of Horticulture at the University of Texas A&M. So here we go.
Hello everyone, I'm Sang-Jun Jung, a PhD candidate in the Horticulture Department at Texas A&M University. Today I'm talking about the interactive effects among light intensity, fired light, and temperature on the plant growth of and secondary metabolites, and I will introduce how we can utilize those environmental factors to improve crop yield and quality. Indoor vertical farming is the promising agriculture industry, which has a great benefit based on their high controllability of environmental factors because the cultivation area is separated from outside. Based on the benefit, the cultivators can produce high quality and uniform crops all year round. However, currently, the indoor vertical farming has one limitation, a low economic viability due to the high initial cost and high production cost for the lighting, heating, and so on. Therefore, improving economic viability is an important mission in indoor vertical farming system. Then how we can solve the problem in cultivation side? One possible way is to reduce production cost by improving crop yield through optimizing environmental factors, which can consequently increase light use efficiency. Previous studies have suggested some practical methods to improve crop yield by regulating light and temperature conditions. For example, some papers report that fard light application can enhance leaf expansion, photon capture, canopy photosynthesis, and finally improve plant growth. In the similar manner, the low light intensity over a longer photo period at the same daylight interval also can improve plant growth by promoting the leaf expansion. Additionally, warmer temperature treatment also can improve crop yield by promoting leaf expansion and plant growth rate. To summarize those experiments, the fard light, low light intensity, and warm temperature treatment can promote leaf expansion, enhancing photon capture and canopy photosynthesis, and finally improve crop yield. However, considering that the different environmental factors improve crop yield in the same way, we can have one question. Is there any interaction among those factors to regulate leaf expansion and final crop yield? To answer our question, though we hypothesize that light and temperature interactively regulate plant growth and morphology. Additionally, in some previous studies, those methods utilizing leaf expansion may decrease secondary metabolite, which is closely related to the food quality. Therefore, our objective in this study was to maximize crop yield by regulating the light and temperature conditions while maintaining plant quality. Although we conducted a series of studies today, I will focus on how the light intensity affect the interactive effects between fard light and temperature in order to adhere to our time limit. In this experiment, we used lettuce, which is one of the most commercially important crop in horticulture. As for the treatment, we had 3 temperature regimes, 20, 24, and 28 degrees Celsius, and 2 levels of fard light, 0 and 20%. We also had 2 levels of light intensity, 150 micromole as the lower light intensity and 300 micromole as the high light intensity. But the period was 24 hours in all treatments. In the result, a left column is for temperature treatment, upper row is for light intensity, and bottom row is for the fard light treatment. As for leaf expansion, warmer temperature significantly increased total leaf area by 121%, and 20% fard light and 20 degrees Celsius can promote leaf expansion by 30%. However, when temperature increased up to the 24 and 28 degrees Celsius, fard light rather decreased total leaf area, indicating that when the warm temperature and fard light treatment were combined under a lower light intensity, they can make a negative effect on the leaf area. However, when light intensity increased up to 300 micromole, fard light consistently increased total leaf area regardless of temperature, suggesting that the diminished the interaction between the fard light and temperature. So dry weight also responded to the fard light temperature and light intensity similarly as total leaf area. Specifically, at lower light intensity, fard light had a negative effect on crop yield under the warmer temperature. However, at the high light intensity, fard light consistently increased dry weight regardless of temperature. Based on the results, under high light intensity, the fard light and warm temperature combination can increase the plant biomass more than 3 times. If we compare with the plant grown at the lower light intensity, the biomass increased more than 6 times. These results suggest that fard light, warm temperature, and high light intensity combination can maximize crop yield through leaf expansion. Also, in addition to crop yield, the combination of warm temperature, fard light, and high light intensity also caused at least equivalent antioxidant capacity and secondary metabolite level. For example, in the left graph for the antioxidant capacity, the combined treatment of the warm temperature and high light intensity and fard light have highest antioxidant capacity compared to other treatments. These results suggest that the combination of warm temperature, high light intensity, and fard light can improve plant crop yield without reducing plant quality. This is the take-home message today. Taken together, we found that the combination of far light, warm temperature, and high light intensity can be effective strategy to maximize crop yield while maintaining the plant quality. This is the last page of my presentation. Thank you for your kind attention. Although I was unable to participate in the real time, please feel free to contact me at the email below if you have any questions. Thank you again. Have a great day. Hello everyone.
Okay, great. So our next presentation is from a PhD candidate who is at Rutgers University in the Department of Plant Biology, and it is Farzana Lubna. And Farzana, we'll call you to the floor to begin presenting.
Thanks, Dr. Madsen. Hi, good afternoon, everyone. So I'm mainly working on the assessing environmental impacts of different lighting systems. And I'm comparing HPS and LED fixtures to know that which one would be more environmentally sustainable and how much impacts they cause to the environment. Next slide, please. Yeah. So why is this research important? The transition to a new technology might feel really appealing, but it's really important to know whether we are truly making an improvement, or is there any additional environmental impacts which is mainly causing harm to the human health or our climate. And also, LED fixture actually advertised as more sustainable than the HPS, or like they have lower environmental impact, but we have to figure out like whether it's true or and in which extent and what other factors might affect in those impact assessment and their extent. So the users phase is really important for these using lighting fixtures like the electricity consumption. So it is also important that the electricity which are generated from different fuel sources, whether they have any impact on the environment and their sustainability, overall sustainability as well. So next slide, please. And we are using a assessment tool, which is called life cycle assessment. And this is a cradle to grave approach, like from raw material acquisition to the manufacturing phase, the distribution and transportation phase, and also the users phase by the consumers, and the end of life treatment, like recycling and incineration, or how you are actually disposing them. So overall, the entire life cycle of those lighting systems will be in consideration while conducting our calculation. Next slide. So we are focusing on 650 watt LED and 1000 watt HPS fixtures, and it was found that they can be used as one-to-one replacement. Like you can actually grow same amount of yield from same area by using this two types of lighting system with the efficacy with their efficacies. And to conduct our calculation, we need to figure out a functional unit, like we simulated a greenhouse tomato production system, and with an annual yield of 60 kilogram per meter square over a 15-year production window. And we are using a calculation software, SIMA Pro, which is a very well-known software for LCA calculations, and using the EcoInvent database. There are like different methodologies out there for impact assessment, and we are using Tracy, but as it is mainly based on it is developed by EPA, Environmental Protection EPA, and also this is mainly based on US locations, and we can actually measure these following impact categories: ozone depletion, global warming, smog, acidification, eutrophication, carcinogens, non-carcinogens, respiratory effects, ecotoxicity, and fossil fuel depletion. So from our initial calculations, we found out that we separated the entire life cycle in 3 phases: manufacturing, uses, and disposal phase. And here you can see that there are these 3 different phases and also the combination of those 3 phases. The LED actually showed 37 to 40% lower environmental impact than HPSS. But from our calculation, we have also found out that the uses phase actually dominated than the manufacturing and the disposal phases, because as the uses phase actually relied on the electricity consumption and heating consumption. So those are very crucial factors in conducting our LC analysis and also measuring the sustainability of these lighting systems. Next slide, please. So there are other several factors that we are considering, that the available sunlight, or DLI, that based on greenhouse locations, and also the crop types, like whether you are using lettuce or tomato, and how much DLI they required, and also the fixture efficacy, and also moreover the overall electricity consumption and additional heating requirements. And also the greenhouse light transmission factors, like whether you are using a greenhouse which has more transmission capability or lower. Those are also actually have significant impacts on the sustainability calculations. Next slide, please. And here from this table, you can actually see that there are these 3 different grids we are considering in our calculation. And the MRO grid, they actually use the highest amount of traditional energy, and the WCC grid use the highest amount of renewable energy, and the NPCC grid use the highest amount of nuclear energies, around 31%. So we use these 3 grids as reference points for these different production sources of electricity. And next slide, please. And from this graph, you can actually see that how the annual GLIs available look like across the USA. Like, though the WCC grid region falls in the same region for electricity consumption from the same different source of electricity sources, but there are differences in their available DLIs, like from 15 to 20 annual DLI to even 50 to 55 mole per meter square per day annual DLI available. Like, there is a lot of variation how much light is available in that particular region, and which is also same for MRO and NPCC. And they have a very significant impact in our environmental impact assessment. So in the next slide, please. And here are our findings from our calculation, that we actually conducted the calculation for HPS fixtures and HPS fixtures, and you can see that the LED lighting we in the NPCC grid had the lowest environmental impact than other grids. And also they have we considered the 60% light transmission rate for the greenhouses, and the results were for lettuce. Next slide, please. And this is the findings for tomato. And same light transmission rate, 60%. And also here you can see that NPCC grid, which actually the production source is nuclear energy, like highest amount of nuclear energy is their production source, and they showed the lowest environmental impact, and then the WCC and the MRO. So as we expect that the traditional energy combined with the location that where you need more energy and more lighting to provide more supplemental lighting is really have impacts, and how they affect our environment and our human health. So these were my presentation for today, and thank you very much. And if you have any questions, please feel free to ask me.
Excellent. Thanks, Farzana. And then we'll advance to our next presentation. This one is from a PhD student at the University of Georgia, Suyun Nam. And I will play a short video.
Hi, good afternoon. My name is Suyun Nam from University of Georgia. Today we're going to talk about energy efficient supplemental lighting control based on light use efficiency. Light environment can be a big limiting factor depending on the location and month of year, and also temporarily the weather condition. That is because we use horticultural lighting widely to increase yield and quality. And also year-round production is possible. But always the problem is high electricity cost. So we have to focus on light use efficiency so that we can maximize the profit and save energy cost. Then how do we control supplemental light levels? First of all, simple control. We can just simply turn on the supplemental lighting in the specific time of day, especially in the morning and the afternoon, so that we can extend the photo period and also increase the DLI, which is accumulated amount of light over a day. And usually non-dimmable lighting is used for this simple control. So it's just on and off system. It's the full power on or off, nothing in between. However, there's more advanced lighting control strategies, which is called adaptive lighting control, which adjusts light levels based on ambient sunlight levels with using the dimmable LED light. As you can see on the right-hand side, depending on the weather, in the real time, this system can adjust the LED light intensities depending on the sunlight level. So for example, when cloudy days, the supplemental lighting will increase or even in the full power. And also when the sunny days, the supplemental light levels will decrease and also even turned off totally. However, we have even more advanced innovative control strategies, which is called light use efficiency based control. This system can adjust LED light levels based on the light use efficiency instead of based on sunlight level. So here, in other words, we can say plant determines the light conditions itself. So here's the picture of the light use efficiency-based control strategies installed in the growth chamber. So using this system, we measure the light use efficiency of plants, which is also regarded as a physiological responses of plants. And the data is sent to computer, and the computer calculates how much light intensity is required for plants. Using this system, we can provide lighting only when plants can use it efficiently, because we're controlling it based on the light use efficiency. So we did a greenhouse experiment to adjust the supplemental LED lighting levels based on a target light use efficiency, which means we try to turn on the supplemental lighting and also increase the light intensities only when the light use efficiency was higher than a specific target threshold. This experiment was conducted in a research greenhouse located in Athens, Georgia, and the LED light was on from 6 a.m. to 9 a.m., which is 15 hours of photo period, using lattice casing for 16 days. And this light use efficiency-based strategies was compared with conventional supplemental light strategies. Now we're going to talk about what kind of strategies I use in the experiment. First of all, simple control. As I mentioned earlier, using this control system, we just added 400 of PPFD over the sunlight in the specific timing, which is 4 hours in the morning and another 4 hours in the evening. Secondly, we use adaptive lighting control, which is supplemental LED light levels and sunlight levels. So some of them was supposed to be 275. So whenever sunlight level is changing over time during the day, the supplemental LED light levels was also adjusted to match the 275. And the LED light was totally turned off when the sunlight alone is over 275. So that is why there are some dots over the 275 in the middle of the day. And lastly, the light use efficiency-based control strategies that is we're interested in. This system turned on the supplemental light when the light use efficiency was higher than 73.5%. So which means we provided supplemental lighting only when plants can use the light energy efficiently, which is over 73.5%. So when you see the graph on the right-hand side, the x-axis is the time of day, and y-axis is the light level, which is adjusted based on the system. As you can see, the light level was decreasing over time in the afternoon compared to the morning, which means plants were having the lower light use efficiency at the afternoon compared to the morning. That is because plants was imposed to the light stress over time during the day, and that was accumulated. So that is why plants can use the light more efficiently in the morning compared to the afternoon. We also harvested the plants at the end of the experiment. All three strategies produce similar average DLI throughout the experiment. So that is because they produce also similar fresh weight and dry weight, but a slightly higher fresh weight and dry weight under the light use efficiency based control system. When it comes to power use and energy use efficiency, the light use efficiency based control strategies use less power, and that produce higher energy use efficiency because energy use efficiency was calculated as fresh weight divided by the total power use. Take-home messages. Plants could control the light conditions themselves by using the light use efficiency-based strategy, and light use efficiency was lower at the afternoon, which means it is more energy efficient to provide more supplemental lighting in the morning rather than afternoon. And the light use efficiency-based control produce higher yield and higher energy use efficiency compared to conventional strategies. And this innovative light control system can be applied to greenhouse production for saving energy costs without harming the productivity. Thank you for my advisors and Project LAMP, which sponsor my research. Thank you for listening.
Okay, good. We're going to proceed to our next presenter, which is Anthony Percival. And Anthony is a PhD student at Colorado State University. Take it away, Anthony.
All right, thanks, Neil. Yeah, hi everyone. My name is Anthony Percival. I'm a PhD student at CSU, and I'm going to talk today about end-of-day far-red light in controlled environments. Next. So just to make sure we're all on the same page, what is an end-of-day treatment? It is a form of photoperiodic light that's low intensity that you apply to extend the day length, and it's usually done to manipulate flowering, either by promoting it in long-day plants or inhibiting it in short-day plants. But the light quality of that end-of-day treatment can also have a significant effect on morphology, and that's really where my interest comes in with far-red light. And then that image in the top right corner is of the photoperiodic lamps we have at CSU. Next. So an end-of-day far-red treatment then is one that is made up of red and far-red light and has a low ratio of red to far-red light because that gives a signal of shade for plants, promoting those specific morphological responses. And down below, you can see what is a typical example of the spectral output of a low red to far-red ratio end-of-day treatment, where you see the red peak and the far-red peak, and you have more far-red light than you do red. Next. So I mentioned morphology, and that's the reason I'm really interested in far-red light as an end-of-day treatment. Because one of those morphological responses is an expansion of leaves, which one of our previous speakers had mentioned. And this can improve light capture and potentially through that improved light capture, reduce production time. I'm particularly interested in applying these end-of-day treatments at the seedling stage when plants have a really low leaf area index, so they have a low ability to intercept that light. One of the complications comes with all the things that can affect responses to far-red radiation, which include things like species, photoperiod, daily light integral, and that red to far-red ratio that's important to actually create the treatment. Next slide. So you can apply far-red light at the end of the day as well as throughout the day, and you can get a similar response from both. But the reason I'm interested in end-of-day lighting in particular is because it's generally more efficient because you don't have to put as much far-red light in to get a similar response, but it also may be less effective at not promoting as intense of a response. But it also might have a specific applicability in greenhouses because it's relatively easy to create that light quality treatment at the end of the day compared to shifting the light quality during the day due to just the abundance of natural sunlight. So that's why I'm sticking with the end of day strategies. Next slide. I'm going to talk about 3 studies that I did kind of from a master's work using end-of-day far-red treatments and what we found. And the first one was with 2 cultivars of Petunia X hybrida that we grew from the seedling stage. We harvested them after 21 days and grew them out in a greenhouse under a fairly low DLI. And we had 3 different end-of-day treatments, which you can see down at either of the figures, one with a red to far-red ratio of 0.8, one with a red to far-red ratio of 0.15, and then another 0.15, but extending it for 4 hours rather than 30 minutes. We found actually that none of our end-of-day treatments had an effect on leaf area, which is the figure on the left showing the leaf area index. But we did find that we saw an increase in stem elongation in response to both lower red to far-red ratios and extended treatment durations. So kind of highlighting some of the effects of maybe when you apply this kind of treatment when you have a low light intensity because it's kind of dual signals of shade. So you're going to get some stretching responses. Next slide. But the thing we also noticed is that we grew these under a pretty low DLI. So we wondered if that was a contributing factor to why we didn't see leaf area expansion as a response. Next slide. So the next experiment we conducted was also with Petunia X hybrida, but instead of growing it out in the greenhouse under a low DLI, we grew it in a growth chamber and made sure it had a sufficient DLI, which is deemed the minimum to produce a quality petunia. And then we also gave that petunia some end-of-day far-red treatments. In this case, what we found is that higher DLI did really limit that stem elongation response, which you can see in the figure to the left, but we still didn't really see a large impact on leaf area. So we didn't know if that was a species-specific thing, or maybe we didn't increase the DLI enough, but it's something we're interested in looking into in the future. Next slide. Yep, and I just said those 2 things. Our last experiment that I'll talk about today is pretty much very similar to the previous one with petunia, but instead we were working with a red leaf lettuce because we were also interested in some pigment level responses. And in this case, we did find an increase in leaf area in response to our end-of-day far-red treatment, which is our figure on the left. And on the figure on the right, you can see a very minimal effect on stem elongation. Next slide. But, oh, sorry, one back. Thanks. So while we did have a significant increase in leaf area, we needed to acknowledge that this was a relatively small increase. And because another effect of far-red radiation is that it makes leaves thinner, that means that light is going to transmit more through those leaves. So even though we got this small increase in leaf area, we weren't really sure if this would make a meaningful impact. So it's something else for us to consider when we're working with morphological responses to far-red light. Next slide. So that's all my experiments I'm going to talk about today. I have some very general key takeaways is that just end-of-day far-red treatments can promote significant morphological responses. So if you are using them as a photoperiodic treatment, to be cognizant of that. And that these responses are affected by a lot of different things, and we don't have a lot of research exploring a lot of these topics. I don't have any explicit recommendations for deploying end-of-day far-red treatments as of now, but I will just say use a bit of caution when you're working with far-red light, especially if light quantity is frequently a limiting factor, because that's, once again, dual signals of shade, so you may get some undesirable morphological responses. Next slide. Just a tiny bit about my future work. We are planning on running some DLI photoperiod experiments and looking at how those affect responses to end-of-day treatments, because those both seem to be kind of key areas of investigation we need to do before we can start developing guidelines for these end-of-day lighting treatments. Next slide. I think that's all I've got. Yep, that's all I've got. Thank you all for listening. I appreciate getting to be here.
Great. Thank you, Anthony. So we will have one more lightning presentation, and then we'll take our group Q&A. And so feel free to keep posting questions into the Q&A. So our final speaker is my own PhD student, Zhao Qi, at Cornell University, who will be talking about his work with far-red light as well. So go ahead, Darren.
Hey, thanks, Neil. Jachi or Darren. So Neil and I have been working with petunia in the past few years, and going to show you some lighting effects on the flowering and plant quality of petunia plants. Next one. Thank you. Okay, so the background is some growers reported delayed flowering in some petunia cultivars, and we proposed a few hypotheses here. The first one is far-red radiation may trigger shade avoidance response and promote earlier flowering. The second one is DOI may also promote earlier flowering and overall plant growth. And lastly, the DOI and far-red may interact with each other. So I'm going to talk about the three consecutive studies we've been doing in the past few years. The first one is in a greenhouse setting, and the second one is in growth chamber. And the third one is a molecular study that we are currently doing following the growth chamber work. Next, please. So for the first study in the greenhouse, we had 2 crop cycles, one in the summertime and one in the winter. We used 3 commercial cultivars. We started with unrooted cuttings. We rooted them for 3 weeks and then pinched them and then put them under the lighting treatments. So we had 4 greenhouse sections with 4 different DOI treatments, 6, 9, 12, and 15 moles. And within each DOI the greenhouse section, we set up 2 growth benches, one with additional far-red and one without. So we grow the liners for 4 weeks under the lighting treatments, and we took some measurements from the liners for the transplants. And then we grow the remaining plants under 15 moles for another 3 weeks. And we did another harvest to assess any carryover effects. Next, please. So here's just a simple diagram showing the setup. 4 greenhouse sections. And in each section, we had either far-red or non-far-red. So 8 treatments total. Next, please. Yeah, so I don't have time to go into the detailed data, but here's the takeaways. If you're interested in any detailed data, I'm happy to talk about that later. So the first and most important conclusion here is the DOI had positive effect on flowering, branching, morphology, and root health of petunia liners, with many effects extending into the finish stage. So that's good. One thing worth noticing is that the liners or the finished plants under 6 moles were a bit too stressed, and most of them are not sellable. So we recommend that growers use at least 9 moles DOI. The second thing is additional far-red may be advantageous because we noticed earlier and faster flowering without a negative impact on the stem elongation. However, this earlier and faster flowering was not necessarily translated into increasing flower buds or increasing open flowers on finished plants, nor enhanced branching or biomass accumulation for some cultivars. So generally, far-red had limited effect in this greenhouse setup, and we think it's because in the greenhouse, the sunlight already has like 20% far-red, and the additional 30 micromoles we gave to the plants was probably washed off by the background lights. So overall, DLI act as a more effective tool than far-red in improving flowering time, flower number, and the overall plant quality in the greenhouse setting. Next one, please. So we moved to study 2 in the growth chamber, and this time we had 3 crop cycles. We had 5 commercial, excuse me, 5 cultivars. 4 of them are commercial cultivars, and 1 is a model cultivar that's typically used for genetic studies. So all the commercial cultivars are facultative long day plants, meaning they're gonna flowers anyways, but the long days can help them flower faster. Versus the mature deploy is an obligate long day plants. In other words, it requires the long days to flower. So we set up 2 growth chambers, one with a high DOI and one with low DOI. We set up the far red bars on one end of the chamber, so that created far red gradients from one end to the other end of the chamber. And we finally got 6 treatments here from 3% to the highest 22%. Next one, please. So this is the setup. The top 2 photos are for the low DOI chamber. We had 150 ppfd, and you can see we got 2 far red bars here versus the bottom 2 are the high ppfd, and we had 4 far red bars. Okay, next one, please. Oops. A previous one. Yeah. The light measure. Yeah, here we go. So yeah, this is the light measurements. So the left diagram is low DOI and the right is high DOI. So as you can see, we double the light intensity in the high DOI chamber. And then in each chamber, there are 6 lines showing different amount of far red. So those are our 6 different far red treatments. Next, please. So this time we started from seeds and we transplant them at week 4. And since then we track the number of flower buds every single day until we harvested each single plant at their first open flower. And then we did some measurements. Next, please. So this is the results. So we took the pictures of the same cultivar when we noticed the first flower on one of the plants. So for example, this first line here, that's for cultivar James. And we took the pictures of all 6 plants on day 52 when we noticed the first open flower on that first plant under 22% far red. So here's the first conclusion, that higher far red resulted in earlier flowering, because you can see all these open flowers on the left side, but not on the right side. And it's true for both DOI conditions. And the other thing I will point out is that higher far red resulted in taller plants, especially that mature deploy at the very bottom. They were very super sensitive to the far red treatments. Then the other thing I want to point out is if we compare the high and low DOI, so the left and right pictures, we can notice that some cultivars actually flowered faster under the high DOI. For example, the mature diploid, we noticed the first open flower on day 59 under high DOI versus under low DOI, the first open flower was on day 65. Okay, so we can move to the next slide. So here are the main takeaways. First, both high DOI and higher far red percentage promoted earlier flowering, or in this case, earlier harvest, without negative impact on the other growth parameters. That's pretty good. And the second thing is high DOI resulted in more compact plant versus higher far red resulted in increase in plant height, but the stretching of most cultivars is within acceptance except that mature diploid. And the last thing is response to far red is linear. In other words, there's not a threshold effect, and growers may choose a combination of DOI and far red based on the flowering time and plant size they desire. Okay, move to the next one. So this is the last page talking about a molecular study that we are currently doing. I don't think I have time to talk a lot of details about it, but the main point is we are quantifying the expression of some flowering related genes in petunia over time and specifically week by week. So the anticipated outcome is that the gene expression could be used for rapid screening in petunia of which light treatments induce flowering. Okay, I think that's the end for my presentation. I'm happy to take any questions.
Great, thank you, Darren. So we did get a few questions that came in, and folks can continue to put them into the Q&A as well. And let's see, one is for Anthony. which was what was the additional increase in power demand by using end of day far red?
Oh, okay. I get the question. So that I think you're talking about that figure with the end of day and the day far red and the control. And what that figure was actually showing was radiation use efficiency. So the higher bar in the for the end of day far red treatment was showing you that you have less input of an end of day far red treatment to get some amount of dry mass than you would a far red treatment throughout the day. And that basically is because for the end of day treatment, you're applying a really low light intensity and getting this some morphological response. Whereas for a far red treatment throughout the day, you're applying a higher amount of far red throughout the entire day. And so that adds up over time. So even if you get a larger response from that far red day treatment, you're still using much more energy to get to that point. Let me know if that clears up that question.
Cool. Yeah, feel free to update Q&A if we didn't get that fully addressed. But thank you, Anthony. That was really good. Then we had another question that came in, which was how to define or how to calculate light use efficiency. And I think that was related to Soo Yun's presentation. So I can take a crack at it unless one of the grad students wants to respond to that. But okay, I'll take that. So light use efficiency, and I have the pleasure of having the slides to look back at. And so what it does is she looks at the total amount of fresh weight that was produced per kilowatt hour of electricity. And another way that it could be defined, but not how she calculated it, could be like plant dry weight or plant fresh weight, again, like plant biomass per mole of incident light or per mole of light the plant received. So then the hard part about, I can't completely answer that question because the photos she showed would show like an individual plant in a treatment. And so we assumed that she probably had to do some kind of scaling, or assuming that a given area would have X amount of plants that would collectively have a certain biomass. So there's probably a little bit of tricky math under the hood there, but in general, it's biomass per unit electricity.
And I guess from the energy engineer, how are you guys in general measuring the energy use side of it? I think the question was like, what are your methods for determining this? So maybe weighing the plant's biomass seems kind of straightforward to measure. How generally are you guys also measuring the energy use of the systems?
Yeah, so Anthony or Darren, do either of you want to take a crack at that? Are you measuring the energy use of your fixtures directly, or doing some like estimates or yeah?
For me, not for this research directly, but it'd be quite easy to measure. It's basically the power times the hours you're running it.
That's right. So in Cornell, often we're not logging electricity use in real time, but we've quantified electrical usage before or after the experiment by using a kilowatt meter to look at current draw or power draw, or we work with our colleagues in Farzana's group at Rutgers University to test light output versus energy use in an integrating light sphere.
So I think that addressed both questions about light use efficiency. The question was like, what are the metrics? How are you measuring or calculating them? And what are some methods for measuring and calculating it? If we didn't address those two questions in the chat in the Q&A, please provide a follow-up question. We did receive a follow-up question for the far red question for Anthony, which is, I think they are curious of like, what was the electrical power usage of the far red product, regardless of the time of day it's being used? Like, are we talking about a 300 watt far red fixture or many fixtures that add up to many more watts? I think the question here is like, how was the electrical energy use increased by adding end of day far red? Without any end of day far red, there wouldn't have been the far red fixtures.
Right. So I guess I'm sorry. Could you ask that question one more time? I'm not exactly sure what.
So as an energy engineer, we think, okay, the grower could grow these products without using far red, and that would be the most energy efficient option because they're not adding an additional fixture that uses more electricity to produce another type of light. I think Leora is asking, when you're adding this far red treatment, what's the electrical impact? Like you said, if end of day far red can be applied for a shorter amount of time, that means you're going to use less energy. But in general, what's the watt impact of these far red fixtures when you're adding them to the system?
So I have to be honest, I'm probably not the best person to actually answer that question. I haven't really looked much into the electricity wattage side of things. But I can say that as like a wavelength or a set of wavelengths, it is far red wavelengths are lower energy. So in theory, you could make a fixture a little bit more efficacious by replacing like a little bit of the white light with the far red light. And that would make it, you would be using a little bit less energy. But that's about as far as I can go into that. I'm sorry, I wish I could comment more on that.
I was asking the
check out the
system.
wattage of the bulb next time you're at the greenhouse. But overall, I think it's
Yeah.
very low wattage. They're not. It's like you said, it's only adding a couple micromoles of light, so it's like 100 times less light than supplemental fixtures. Is that right? Yeah.
So for like the layman, if we're talking about a horticultural light fixture typically used for top canopy lighting, that could be 300, 500, 1,000 watts. A far red light, Neil, would it be closer to 50, 100 watts?
Yeah, probably like 10 to 20 or something like
10 to
that.
20. Okay.
Yeah.
Cool.
About
Well, we
100
went into the
times
weeds
less.
with that one.
I had one question for Farzana. So Farzana, in your calculations, you had to, you assumed that a fixture could be used for 15 years lifespan. And is that realistic for LEDs and for high pressure sodium lights? And then for high pressure sodium lights, do you consider like changing up the bulb of the fixture as well?
Okay, thanks for your question, Neil. So for LEDs, it was assume that they can last for 15 years because they have very high life expectancy. But for HPS, you have to change it like in every 3 to 4 years. So we actually calculated like how many bulb replacement is required in that case. So we found out that it's like 4.5 in 15 years window. You have to use and replace the bulbs for HPS.
I see. Yeah. And then do you consider that in your calculation too, like the embodied
Yes.
energy in a new bulb? So
Yes.
yeah. Okay. Yeah, very good. It seemed like every environmental metric, like if you actually operated them over 15 years, every environmental metric was better for LED. Was that right? Yeah. Cool. Do any of you have questions for each other?
We just received another one in the
Oh,
chat.
great.
While you guys are thinking of if you have another question for each other, question for Farzana, did you look at the seasonality of the fuel mix in addition to annual analyses?
If I could interpret that question, I think it means like during certain seasons, if there's going to be more peak energy demand, they might have to use temporary power plants that burn fossil fuel to add more energy to the grid. And then during other seasons when less power is needed by the grid, then like the nuclear or hydroelectric might provide more of the base power.
Okay, so in my calculation, we have like calculated like how like we figure we figured out some reference points like 10 to 15 point locations in maybe WCC grid, and on those locations, like how much DLI is available, like in January, in February, and in March, and also like during summer months, you can skip providing any supplemental lighting because the natural light is already available there. So we have considered those season based, like how much and supplemental light you have to provide. And about the mixture, the thing, if I'm getting it right, the question that are you referring that if there is any chances that we could actually go for like nuclear power during winter months and something like this, or no?
Yeah,
It's
I guess
more to-
I think your
Okay.
results kind of use the average mix of the grid over the
Yes,
course of a year,
yes,
not
yes.
fluctuating day to day.
So the things in the WCC grid, you have these commercial, like you have already those electricity available in the, in those areas that they produce this electricity from these different sources. And in Northeast region, they produce it in different sources, but I don't think it is possible that actually you can change what kind of electricity you want to use. But there are these long-term goals that the grid electricities are changing, they're updating. In Northeast regions, there are like lots of solar powers are being used, and even in some greenhouses, they are actually installing solar powers, though they can actually use those renewable energy instead of using the grid electricity. Those are actually available in those particular areas. So by this way, maybe you can go for renewables choices.
Mm-hmm. Yeah. And I think Leora has a follow-up, but maybe in the interest of time, we'll connect you two together. I think you two would have a great conversation. Leora's great in this area of energy usage. And then Sheila also had a bit of a follow-up question related to light use efficiency calculations. I think that one also referred to the third treatment or the less treatment in the University of Georgia work. They were actually measuring photosynthetic rate of the plant. And so when photosynthetic rate went down, and I'm not sure exactly how they measured that. Sometimes in their research, they use electron transport rate as a proxy. So plants kind of, after they've been photosynthesizing for several hours, they get sometimes stressed out or they have oxidative stress. And so then photosynthetic efficiency can go down in the afternoon. So I think that relates to the University of Georgia work. But Sheila, we can connect you directly to that researcher there.
Well, I think it's best if I actually get the answer for everyone who attends the webinar. So I'm going to email both of those questions to Soo-Yun, and when I follow up with the webinar recording, I'll share it. So in case anyone else is interested, if you're watching this, I'll try and get this information for everyone. I think it's of interest to me as well. So I'll follow up with everyone on that one. And thank you very much for the detailed questions. A little chat in the a note in the chat is talking about how you can see the hourly generation mix of different utilities depending on the region. So that might be something, if you aren't aware of, to use in your research. Thank you very much for your attendance. And again, I'd really like to thank all of the researchers who shared their findings and showcased how growers can hopefully adopt this sort of technology with more insight and not have to try it and make too many experiments themselves. They can learn from yours. So, Neil, do you have any parting words?
Yeah, maybe
something about LAMP.
Thank you for joining us. You can find more about LAMP if you go to the Project LAMP website, and we can share that in that follow-up email that Gretchen's going to send out. But it's hortlamp.uga.edu. So hortlamp.uga.edu. There's a bunch of these research briefs and lighting calculator tools and things